another building procedure today. Our last talk of today is through process modeling of fracture toughness test of multipass welds incorporating residual stress distribution.
Thank you, Chairman. Good afternoon, everyone. My name is Mikami from Osaka University. Today's my presentation is about the numerical simulation of CTOD testing considering residual stress distribution by multipass weld. So at first, I'd like to explain the background of this study. So in fracture toughness test, fatigue pre-cracking is required by the testing standard. In the test of multipass weld of steel plates, non-uniform fatigue pre-crack front is often obtained due to the residual stress distribution. This picture shows a typical example of non-uniform fatigue pre-crack front. This is caused by the welding residual stress. So if the pre-crack front is curved like this, the result of the fracture toughness test shall be considered as invalid when the extent of the curvature exceeds allowable limitation specified in the testing standards. So residual stress modification is usually performed before introducing the fatigue pre-crack. So this slide shows the typical method to modify the residual stress distribution caused by welding. However, even after this treatment, the resultant residual stress distribution depends on the treatment condition and cannot be completely zero. So the residual stress may affect the CTOD testing result. So the purpose of this study is these 2 points. First one is clarify the variation in stress distribution during specimen preparation. So welding and machining, and then stress modification and pre-cracking. We trace the variation in residual stress distribution, and then investigate the effect of residual stress distribution on the CTOD test result. We focus on these 2 topics. So this is the outline of this presentation. And at first, we fabricated a multipass welded joint. The weld residual stress distribution is an important input in this study. So, in order to consider the valid residual stress distribution in the simulation, we first fabricated a multipass welded joint and measured the residual stress distribution. This is the geometry of the fabricated multipass welded joint. This has the weld length of 500 millimeters and the thickness of 50 millimeters. And this is the macro cross section. And the steel used was the typical thick building steel. And then welding was performed by FC8W. And then welding condition is summarized here. And then the residual stress distribution was measured by strain gauge technique. The strain gauge is attached to the specimen, and the specimen was cut into the small pieces, and then relieved strain was measured by the strain gauge. And this graph shows the residual stress distribution through the thickness. And this is the bottom and this is the top, and then two components. So one is longitudinal stress, and then transverse stress is displayed in this graph. So in this case, the welding performed in X direction. Therefore, if we test this specimen, the pre-graph is introduced into the X direction, so along the welding direction. So the component in transverse direction, the residual stress in transverse direction is important to the propagation of fatigue pre-crack. So the residual stress in transverse direction is tension at the top and the bottom surface and compression in the mid-thickness. So this will retardate the fatigue pre-crack extension at the mid-thickness. So now we fabricated the welded joint and measured the residual stress, and then we reproduce the residual stress distribution by simulation. So this slide shows the finite element model of the welded joint. The geometry and the size is the same as the fabricated one, and also the path sequence is also determined based on the experiment. And this is the material properties used in the welding simulation. And then in the welding simulation, phase transformation and the temperature-dependent material properties were taken into consideration. And this is the result of welding residual stress simulation. So this is the longitudinal component, and this is the transverse component. And this graph shows, this figure shows the distribution at the center cross section of the welding length. So as you can see in this figure, this is the transverse component, tension at the top surface, and then compression in the mid-thickness. And this is the comparison between the experiment and the finite element simulation. So the reasonable agreement between experiment and simulation are obtained. So now we get the welding residual stress distribution by numerical simulation, and then we go into the through process simulation of CTOD test. At first, the residual stress distribution obtained in this specimen welded joint was applied to the specimen for CTOD testing. So this CTOD test specimen had B times 2B standard shape of the CTOD bending test specimen, and then the residual stress is mapped onto the specimen model. And the extra part of the welded joint was neglected during the mapping procedure. So this corresponds to the cutting off the specimen from this welded joint. And then this slide shows the mesh division for mapping. So this model had the mesh division of this figure. And then the figure on the right-hand side shows the detail in the notch. the notch part is initially meshed, and then in front of the notch root, duplicated nodes are generated. This is because to model the notch introduction and then pre-crack introduction. So the notch part is deactivated to model the notch introduction, and after that, the pre-crack, these duplicate nodes are separated to model the pre-crack introduction. So I'd like to show the residual stress distribution throughout the simulation process. At first, this is the mapping result. So this is the residual stress distribution after cutting off the specimen, this side of specimen from the multipass welded joint. And then there is no notch and then no pre-crack at this stage. And this figure shows the center cross-section through the thickness. So mid-thickness is shown in this figure. And then the notch part is machined by deactivating the element corresponding to the notch shape. And then redistribution can be calculated as shown in this figure. And then this is the residual stress modification process. Reverse bending is applied. So this is reverse bending, so the notch part is compressed like this. So the compressive stress is occurred in the notch root. And then after that, the reverse bending is unloaded. And then the compressed part changes to the tensile stress. And after that, the pre-crack is introduced from the notch root, and then the residual stress concentration moves to forward. Okay. And then this is the final state, 3-point bend testing simulation. And this is the distribution in the center cross-section of the specimen. Initially, as welded condition, the residual stress is tension, compression, and tension. However, after the reverse bending, the notch root becomes all tension. And this is the residual stress distribution in front of the notch root. So by reverse bending, the residual stress becomes tensile and uniform through the thickness. So this is the effect of the residual stress modification process. And then this is the result of the 3-point bending test simulation. This graph shows the relationship between rod and notch mouth opening displacement, PVG relationship. So these three graphs show the base metal, no residual stress, and the as welded displacement and the reverse bending displacement. So these are quite similar in this graph. This is because the change in the residual stress distribution is limited to the notch root. However, even if the PVG relationship is like this, the notch crack opening profile is very different. This is the base metal without residual stress, and this is the as welded displacement. So the crack opening shape is strongly affected by the residual stress distribution. And this is the reverse bended displacement. So in this case, the residual stress is modified, so the crack opening profile is similar to that of base metal. So this is the summary of my presentation. And thank you very much for your kind attention.